Hello, my name is Ciera Hudson, and I'll be discussing the magnetic field of a bar magnet experiment. In this lab report, I will be analyzing the magnetic field created by a single bar magnet. First, I'll use a bar magnet and a smartphone magnetometer app recording distance and direction of the smartphone with respect to the magnet, as well as the determined magnetic field at each of these locations. Afterwards, I'll be creating a computational model that displays arrows showing the magnetic field at several different locations. Additionally, I'll be answering a couple of conceptual questions that further our knowledge of magnetic fields. Before collecting any experimental data, it was necessary to compensate for Earth's magnetic field so that it couldn't cause distortions in the data. This means that the magnetic field being measured must be orthogonal or perpendicular to Earth's magnetic field. To do this, I slowly rotated my phone until the x component of the magnetic field that was measured was equal to 0. Then, I set up the bar magnet and meter stick in relation to the smartphone as shown in the upper right-hand corner of this slide. After that, I needed to find out where the magnetometer is located in my phone. To do this, I slid the phone back and forth perpendicularly to the meter stick until the absolute value of the x component was at a maximum and the absolute value of the y component was at a minimum. This allowed me to verify that the magnetic field was being recorded exactly to the east of the bar magnet. For the data collection, we were provided with an Excel spreadsheet that would average data values and display a linear regression of our data. The first step was to find the horizontal distance that the smartphone would need to sit away from the magnet to output a given value for the magnetic field. The values that were expected were 20 microteslas, 70 microteslas, 120 microteslas, 170 microteslas, and 220 microteslas. The spreadsheet averaged these values and plotted them on the graph, which will be shown in the next slide. The next part of the experiment required the phone to be at a 45-degree angle with the bar magnet. To find the horizontal and vertical distance for this measurement, the horizontal distance was recorded where the magnetic field read 100 microteslas. Then, the phone was moved upwards by the same distance to collect data at this location. Afterwards, I added the y component of the Earth's magnetic field to the y component of the measured magnetic field to correct for Earth's magnetic field. Here, you can see the tables of values that were collected in the experiment. The upper left table shows the values of the distance and measured magnetic field, averaged from 3 trials each to lessen any effects of outliers. Then, the ln of the distance and the ln of the magnetic field were both calculated for each value and put into the graph on the right. As you can see, the graph data is almost linear, and the equation for the line of best fit is displayed, which is y equals negative 3.2665x minus 0.9858. These values will become important when we make calculations for the computational model. At the bottom, the data is displayed from the second configuration of the smartphone and magnet, where the total distance d and net magnetic field are displayed. Now, let's talk about the concepts that will be used in this lab. The first one is this Biot-Savart law, which determines the vector of the magnetic field that is created. It relies on the distance between the location vector r and mu. Additionally, it's proportional to the magnetic constant shown at the bottom of the screen, which equals 1 times 10 to the negative 7th. The second equation is for the magnitude of the magnetic field caused by a bar magnet. This equation states that the magnetic field is equal to proportional constant k times r to the n. We already found the value of n during data collection, so I'll show you how to derive k from this value in the next slide. Now we can discuss values that were found from the experiment. The value of n was found to be negative 3.267, which was the slope of the line of best fit from the graph. We would expect it to be negative 3 because r is typically raised to the negative third power in the Biot-Savart equation. Therefore, I recorded an error of 8.9%. I then needed to calculate the value for k that would be used in the model. Since ln of k was equal to the y-intercept in the graph, I set it equal to negative 0.9858 and solved for k. Then, I rearranged the equation to find mu for the computational model. The next step was to edit the starter code on GlowScript to create the computational model of the magnetic field. Several changes that needed to be made were the inclusion of the Biot-Savart law that we discussed previously, the location vectors for 6 of the arrows in the model, excluding the one that will be sitting at a 45-degree angle from the bar magnet, the value of k, and the equation for the magnitude of mu that we found in the last slide. The other changes were related to actually creating the arrows that would be displayed in the model. I set up the code to run the Biot-Savart equation for each arrow. This occurred for 2 on-axis locations, 4 perpendicular locations, and 1 45-degree location. Here, you can see the model as it runs. The arrows are placed around the model to show the magnetic field at various locations. You can see that the arrows at parallel and perpendicular locations are in opposite directions, mimicking the field lines of a magnetic field. The parallel arrows have a greater magnitude, as we found in our physics class. The arrow at the 45-degree location is pointed away from the model, showing the correct magnetic field at that point. The vector values of each location are shown below the model. The first conceptual question that we were asked to answer is what would happen if we hadn't lined the phone up to compensate for Earth's magnetic field. In this case, the x component of the field would be partially due to Earth's magnetic field and not just the bar magnet, so it would have distorted our data. The second question asks how the magnetic field would have changed if we had instead used 2 bar magnets lined up next to each other instead of just one. Using 2 magnets would have resulted in a magnetic field that would be twice as strong because the value of mu would be greater. However, the direction of the magnetic field at each would have stayed the same, assuming that the magnets were lined up in the same orientation. In this lab, we were asked to run an experiment calculating the magnetic field of a bar magnet at varying locations. At first, the magnetometer app that I was using was not correctly reading values, so I had to download a different app, which appeared to work much better. Then I successfully recorded all the required data and generated a plot of values to help us model the field. Then I coded the GlowScript model that would display direction and relative magnitude of the magnetic field at 7 different locations. This model was successful as it behaved how we would expect it to. Thanks for watching!